Good morning, good afternoon, good evening, everyone. In fact, for some of you, it's probably good night. But thank you so much for investing your time with us today. My name is Reginald Hammah, and I'm the technical chair for the conference and the moderator for this session. Today, we have an excellent panel titled, Is Numerical Modeling a Solution or a Problem? We'll be talking about the geotechnical industry's efforts to appropriately use numerical modeling tools and how we can advance the state of the art. Now, this question is a question that impacts all of us in what we do. Are we using numerical models really in a way that gives us solutions, or they actually cause us problems? So my hope is that you'll leave here today, after we're done with the discussions, with new thoughts, fresh perspectives, new strategies of modeling that will make us very successful in our geotechnical business. So I'm going to describe the format a little bit just to give you an idea of what to expect. I'll briefly introduce each of the panelists, and that will involve telling you a little bit about their background. And then each panelist will present their position on numerical modeling. And once we do that, we will kick straight into the debate section. We'll probably start with a few questions to get things going, but we'll be taking a lot of questions from the audience. So please feel free to type your questions as we go along. And then once we are done, once we finish with the position papers, as we say, we debate, and then we will wrap up at some point. I hope that sounds good to you. And so let me get started with the introductions. The first person I will introduce is Dr. Joe Cavallo. Dr. Cavallo is a principal of Golder Associates in the Mississauga office in Canada. He's a rock engineer and a fracture mechanics specialist with over 30 years of experience in the field. Joe graduated from the University of Toronto in 1982 and got his, that was with a bachelor's, then he got his master's and PhD degrees from the same university. In 1988, he moved to Tulsa, Oklahoma, where he was a research scientist with Dawel Schlumberger for approximately 2 years. Then he moved back to Canada to work with Dr. Brettas on developing software funded by the Mining Research Directorate in Ontario. He was the principal developer of phases, Onwedge, which were all developed under contract to the Mining Research Directorate, and he also had significant input into the development of Examine 2D, S-Wedge, and C-Pillar. Once that program was done, Joe joined Golder Associates and has been with that company since then. The next person I will introduce is Professor Dick Stacy. Professor Stacy initially graduated as a mechanical engineer with particular interest in stress analysis. Then he worked under Dick Benierski in the rock mechanics division of the CSIR, the National Mechanical Engineering Research Institute in South Africa, before he spent a year at Imperial College as an academic visitor in the engineering geology department. He spent 25 years with SRK Consulting and was chairman of the South African company before joining the School of Mining Engineering at the University of Witwatersrand in 2000. As Centennial Professor of Rock Engineering. He retired at the end of 2008, but he continues to participate in the school. And he has a doctorate in rock engineering and 50 plus years of experience in rock engineering. Next panelist I'll describe is Tiago Brettas. Tiago is from Brazil. He graduated with a degree in civil engineering from, forgive my Portuguese, Universidade FUMEC, and graduated with a degree in structural and foundations engineering from UNICIT. He then obtained an MSc in geotechnical engineering from UFOP, and Tiago has over 19 years of experience in geotechnical engineering, especially in 2D and 3D numerical modeling of dams, piles, waste dams, open pits, and stabilization systems using both limit equilibrium and numerical methods. Then, last but not the least on the panel is Dr. Brent Kolkum. Brent earned his bachelor's in 1984 in geological engineering, master's in 86, and PhD in 96, all from the University of Toronto in Canada. Brent has many interests, including numerical modeling, all the numerical methods essentially, slope stability, and one of his babies is data visualization. Now, let me tell you, with Brent, I can tell a few personal stories. He started programming in 1987 when he took a course with Professor John Curran on numerical methods in geomechanics. These were the very first days of the PC. So John asked him to create a version of a Unix program called Mind5 for the PC, which he did. And that's a dream we are living today. Now, he helped lure me to the rock engineering group at U of T when I was doing graduate studies, when he used a device known as the spaceball. The group had been researching ways in which users could easily manipulate geometries in 3D on silicon graphics computers. He saw the device at a SIGGRAPH conference and knew that he had the answer. So he asked Professor Curran to buy it, and John kept on putting it off. So what did Brent do? He wrote a script to send John an email every day to remind him to buy the spaceball. Not too long after that, John came and told Brent, stop it now, I've ordered the spaceball. And that is how he got into 3D visualization, and he's been at it ever since that time. 35 years he's been doing this stuff. And then I'll also be helped to help me moderate is Dr. Alison McQuillan. Alison is the director of Rocscience in Australia, and she's based in Gold Coast. And she provides a lot of software training and technical support for people in the Asia Pacific region. She's a chartered professional geotech and registered professional engineer in Queensland. She has a master's of mining engineering in geomechanics from the University of New South Wales, and recently completed her PhD in rock mechanics at the same university. She does a lot of open pit slope stability stuff, and I'm sure some of us heard her speak this earlier today. So thank you very much. These are the people who will be participating in the panel. But of course, there's another important group of panelists, and that group includes each and every one of you. So as we debate through the topics, please feel free. It's not only questions you can ask, you can also contribute ideas. We'll see them on the conference platform, and I'll read them out for everyone to hear. So that's how we're going to go. I will now ask our excellent technical coordinator, Calvin, to start taking us through the position papers. So Calvin.
Thank you, Reg, for that nice introduction. I've got maybe 4 or 5 slides to show my position paper. We can go to the first slide, please. You're probably going to feel like this is a broken record because it's been said many times today. But although there is a lot of science and technology behind modeling, I look at modeling, it's still an art, okay? And it's the art of identifying mechanisms and then quantifying the sensitivity to those controlling parameters. And it is an art because you have to be inquisitive, you have to look at the right parameters and the right combination to understand. And the idea here is to actually get a hold of the mechanisms, to understand the mechanisms, because if you can't diagnose, you can't cure. So that's the main thing. My first slide and my last slide are probably the most important. I have some very, very basic rules for analysis. If you do not understand the tool, you shouldn't be using it. So you should actually, get yourself acquainted with the capabilities of the tool and the limitations of the tool. You need to select the right tool for the job. You need to understand the range of application of that particular tool. And you need to understand the required input parameters. And as it was said before by Dr. Diedrichs, beware of default values because they will come back to haunt you. So the other thing to understand is that there is no absolute result. No result is absolute. Everything is relative, and take it with a grain of salt. Make sure that you are inquisitive enough and have enough skepticism to question the results. The other very basic concept is you should walk before you run. Start with a simple model. There's nothing wrong with starting with a simple model. Do not use complex constitutive models that require parameters you do not have. That's just not feasible. I'll give you the corollary for that is if your problem is indeed complex, then you need to go and get the right data to actually solve that problem. So these are very basic, and they sound a little bit philosophical, but they are the basis of good modeling. Next, please. So one of the questions that's being asked today here is, are these tools helping or are they hindering? And it's been said again, like I said, it sounds like a broken record. We cannot deprive competent users of numerical tools just because some people will misuse it. Technological advances inevitably get used for wrong purposes, and I see malevolent here as well. I don't think that's the case in our industry, but they do get misused, and that's no different in our industry. So we have the responsibility to minimize misuse. Now, it's an open question on how do we do that. Does that rely on educational institutions? Is there some kind of collaboration between software developers and educational institutions? What is the right mix here? What's the right combination so that we can help people, use these things and minimize misuse? Next slide. On dimensionality and use of 2D, 3D, and I'm going to include geometry in this slide. So often problems are three-dimensional in nature. I mean, they all are. We look at portals, connections, intersections of tunnels. These are truly 3D problems. However, we can use 2D in many, many instances, but it's necessary to understand their limitations. And we need to complement this with such methods. We've created some, for example, ground reaction curve methods to account for the 3D effects of a face. And we can learn from that and include them in 2D methodologies. The other misconception out there is that, 2D is always more conservative. It gives you, lower factors of safety. That is not always true. Do not believe that, the 3D analysis is always going to give you higher factors of safety. That is not correct. Now, 3D model building is more complex, obviously, but the tools have evolved to the point where, they are now routinely used in engineering. And I just want to say something about geometry. There is a lot of heartache you can mitigate with geometry. Geometry to me is king. You can deflect stresses by using proper geometries in your open cross sections. You can, that's seen in block caving and the selection of draw points and spacing between draw points. So everything revolves around geometry. Don't ever discount geometry to help you mitigate problems when you're looking at them. Next slide, please. And then we come to reality. How can we bring in more reality into the models? Rock is not continuous. Rock is not isotropic. So we are used to using these models with constitutive models that are made for continua, and there is no real 3D anisotropic plastic model today that is really widely accepted. And what that does is that it makes us rely on joint networks, on explicitly including faults and joints into our models. So until such time we can include some of these anisotropic traits into continua, we'll have to rely on the joint networks. I want to talk a little bit about shear strength reduction. Shear strength reduction is now a state of practice, especially when evaluating slope stability, but you need to exercise some caution because you can very easily switch failure mechanisms as you are reducing the shear strength. So you have to be aware that when you look at these results, you are comparing apples with apples. So look at your results carefully, make sure that everything is monotonically changing and you're not actually changing mechanisms that will not allow you for proper comparison. And this is my last slide is coming up, and this is very important for my business and the business I'm in. In the design process, the calculations are verified and reviewed by senior staff or by review boards. And numerical modeling is much more difficult to verify than the old ways we used to do calculations. Next slide, please. So there's a particular challenge because in traditional reviews, calculations that come to you on a paper. You could follow them. You could do side calculations on your own, verify numbers. And these things are not readily transferred to numerical models. All of the calculations are hidden in the model. Even input parameters. You may go through the input parameters and verify them and vet them for the model, but you never know if they were input in the model properly. So you always have to dig into the models and make sure that, yeah, I really did use the correct parameters in the model. This is very challenging, which comes to this idea of QA/QC for modeling. And I stole this next bullets from a report from the Department of Education in the UK on principles of QA for modeling. You need to verify the models. You need to verify that they're being built right. So verification, the question is, has the model been built right? You ensure the model is implemented correctly. You have a second model or a peer check it. And then you have validation, which is a question, has the right model been built? Ensure that the model appropriately represents the problem. You have not built a model that is not representative, and whatever results it gives you has nothing to do with what you're trying to solve. So you need to understand the quality and the limitation of the data, as well as the assumptions in the model. So verification and validation, and this was touched upon this morning or yesterday by Dr. Bodden. It's the two components of good QA/QC. And with that, I think I'm going to leave you and let the next presenter go ahead and do their position paper.
Thank you very much, Dr. Cavallo, for expounding what your position is on numerical modeling. Start simple, learn to walk before you run. That sounds like very good advice. But I hope everybody is making notes, and we're going to ask some interesting questions. And please feel free to also challenge any positions if you think that something contrary ought to be done. Next, we are going to hear from Professor Dick Stacy.
I'll start by, I think, giving some things that I think are really important. And the first one is that consideration of Beniowski's design process is a very important part of numerical modeling. And also the modern numerical modeling philosophy that was published by Starfield and Kundal back in the 1980s, I think is still extremely valid. Next slide. This shows a version of Beniowski's design process, and the steps 1 to 10 are all very important. As far as numerical modeling is concerned, steps 1 and 2 deal with the problem statement and any things that curtail that. And that's extremely important to define clearly what the problem is and how you're going to go about that. And then step 4 is effectively the geotechnical model, and that is understanding what you expect to happen in practice and how you think your model will behave. Then steps 5 to 7 are the actual modeling, there's optimization, and ultimately you need to monitor to check that what you've been predicting or you're analyzing in fact is realistic. Next slide. Just to pick out some of Starfield and Kundal's numerical modeling philosophies and compare that with Beniowski's process. As I said, step 1 deals with the clarity of design objectives, and that corresponds with Starfield and Kundal's statement. Be sure before you start that you are quite clear about why you are building a model and what questions you are trying to answer. And then, as I mentioned, step 4 in the design process corresponds with look at the mechanics of the problem. Try to identify important mechanisms, modes of deformation, and likely modes of failure. Beniowski also specified principles, and one of his was the simplicity principle, and that corresponds with Starfield and Cundall's design or borrow the simplest model that will allow the important mechanisms to occur. As I said, steps 5 to 7 of the design process involve the running of the models. Step 8 implies multiple models, and that corresponds with Starfield and Cundall's statement. It should also be noted that implicit in the above guidelines is a rule that rock engineering models should never be run only once. It is in the sensitivity of the results to changes in parameters and assumptions that the model is most informing. Next slide. Another point that I think is extremely important is the value of simple elastic modeling. And again, that corresponds with the design statement, design or borrow the simplest model. Excavation in rock usually involves unloading of the rock, certainly in at least one of the stress directions. And behavior is commonly linear in unloading, hence the value in elastic modeling. Doesn't mean to say that you will have the same modulus or directly the same behavior, but if it's linear, then linear modeling is going to be very useful. Next slide. The importance of three-dimensional analysis. I think this has been emphasized already, but just a point about strength of rock and rock masses. All rock engineering problems are actually 3 dimensions, 3D. And an example here in this graph just shows that rock strength, when tested in 3D, that's with sigma 1, sigma 2, and sigma 3 acting, is very different from what it is in 2D and in triaxial testing. You can see the dashed line going up towards the top. That's the triaxial hook brown. The horizontal dashed line is the polyaxial hook brown, and the real behavior you can see by the dots, the points. Next point, next slide. If you look at the 3-dimensional strain stress matrix, you can see that there's actually 6 moduli elements and 3 Poisson's ratio elements. And therefore, single values of E and Poisson's ratio in analyses, as we commonly use, sometimes could be misleading. And I've never heard of anybody measuring a 3-dimensional Poisson's ratio or a Poisson's ratio for a rock mass. Next slide. Just as an example of that, synthetic rock mass analyses of an anisotropic rock mass. And here you can see stress strain results at different angles. And you can see how both the modulus and the strength of that rock mass are different in the different directions. Next slide. So numerical models must take jointing into account because it's the joints which are going to affect the behavior. But we don't know their actual orientation except where we can see them on the surface where they're exposed. So within the rock mass, we don't know what the persistence or spacing is of each joint set. We only know the statistical variations. And therefore, we need to carry out numerous analyses to take into account the variability. Next slide. Just a point about rock masses and rock mass behavior that one often sees published in the literature. And I've seen this on numerous occasions where behavior is assumed. In other words, a criterion is assumed. And there's real data and the properties of the rock mass are adjusted until there's a match with the observed behavior. And then the assumption is made that the modeled rock mass properties are correct, and that they can be used then for analysis of further situations. And that's just not true. Although I would say that if you're using that for design purposes with a factor of safety, it might be okay. But usually it's not valid for the prediction of behavior under new conditions. Next slide. So numerical models must take into account the failure mechanisms and rock fracture. And fractures may initiate due to one criterion, propagate due to the same or other criteria, and failure then may develop due to yet other criteria, including structural criteria such as beam bending, buckling of rock plates or beams, and prediction under such circumstances presents a significant numerical modeling challenge. I think that's my last one, yes. So that's my thinking on the subject.
All right, thank you very much, Professor Stacy. And in some ways I can see certain themes are recurring. They need to start simple, they need to use simple tools, they need to be careful about calibration and all that. And we'll expand on these as we go along. I will now invite Tiago Brettas from Brazil to give us his perspectives. But before you launch into your presentation, Tiago, how do I pronounce it? Is this Universidade or Universidade?
University is Universidade.
Uni, all right, okay, thanks.
Okay, hello everyone. I'm going to talk about the challenge in tailings dam modeling. And first, I'd like to let's briefly talk about two cases concerning tailings dams, just to understand tailings behavior's complexity. After two major tailings dams accidents in Brazil, especially the one in Brumadinho in Minas Gerais state, efforts to better understand iron ore tailings behavior have increased. Due to hydraulic disposal and the mining front location, tailings heterogeneity is difficult to characterize. However, these characteristics are crucial for evaluating safety conditions. Next slide, please. Fundão tailings dam breach by liquefaction on 2015. Accident with the greatest environmental damage in the history of Brazil. Brought some questions about how we assess tailings behavior. Saturated sand tailings in loose state, which exhibit contractive behavior, were deposited by hydraulic means. For liquefaction of these tailings to develop, a trigger to mobilize undrained shear and hence flow sliding was needed. The Fundão Tailings Dam Review Panel concluded that a lateral movement accelerated by an earthquake occurred just before the collapse contributed to initiation of the failure. Evaluating the potential trigger mechanism, the panel concluded that lateral extrusion initiated the failure. The lateral extrusion mechanism develops as the dam increases in height, loading the slime-rich layers vertically, which tends to spread laterally, rather like squeezing a toothpaste from a tube. This results in stress changes in the overlying sands, which reduce their confinement, leading to collapse. We can see here some tests in Fundão Dam tailing. On the right, we can see a triaxial test where we see a representative instability line varying the void ratio of those tailings. And we know that increasing the void ratio, we get a looser state, and so more contractive will be the tailing. And on the left, we see stress strain, varying the deviator stress, and the red line is indicated the tailings with the biggest void ratios. We can see a sudden post-peak loss ratio on the red lines indicating the loose state. And now the next slide, please. Yeah. Now concerning Feijão Dam 1, the panel report titled Technical Causes of Failure of Feijão Dam 1 in January 2019 indicated that other factors also influenced the collapse. Flow liquefaction of the mostly loose, saturated, heavy, and brittle tailings took place in the marginally stable dam. The amount of strain required to trigger the sudden loss of strength, liquefaction, in some tailings reservoirs regions were very small. The critical combination in this case was the internal strain due to creep, intense rainfalls, the dam's design with steep upstream slopes, and a flawed internal drainage system. Brittle tailings behavior due to bonding. This tailings specifically has an iron ore contact over 50 or 52%. So this amount of iron on the tailings created a bonding, but it's quite a fragile bonding that create a brittle behavior of the tailings. The evaluation of safety includes identifying different tailings domains in the reservoir and analyzing their behaviors. We can see here a CPTU test with the contractive behavior in the state parameter, where we can see also an increase of the pore pressure. And on the left, we can see also a stress strain from a triaxial test with a sudden loss of strength and almost non-residual strength. So we try to identify those signatures of the behaviors on the tailings and try to separate layers with different signatures on the cross sections we are going to analyze. Those signatures we try to separate regarding dilative contractive response, pore water pressures, strain softening behavior, and so. Tailings are so grouped into domains with similar characteristics. Although there is significant uncertainty regarding tailings behavior, numerical modeling can help geotechnical engineers to simulate and estimate tailings stress strains. Next slide, please. We can see on the left a calibration of a north-end constitutive model for an iron ore tailing using RS data. We can see axial stress strain, and we can see the calibration for a deviator stress of 800 kPa. But it's challenging to represent a strain softening response with different post-peak loss ratios, depending on the deviator stress of triaxial tests. After calibration, numerical modeling can be conducted to assess the stress strain results and verify the possible formation of progressive failures, excess pore water pressures, yielded elements, and others. So the numerical models starts on the field. I think that's the first step to start a numerical model. It's recognize the structures we are going to deal with, and then plan a good investigations and plan our lab and field tests. And then we go back to the office and analyze the results. So analyzing the field and lab tests, we can identify those tailing signatures and create those different domains concerning the behavior. We can see very different strain softening responses with different post-peak loss ratios. And so the uncertainties around the tailings behavior and failure modes complicate numerical modeling. They affect the ability of engineers to predict and monitor creep movements and progressive failure and lateral spreading. Not necessarily use complex constitutive models leads to good results. Those complex constitutive models has a lot of specific inputs that they are not easy to get. However, the questions are we correctly evaluating the safety of those dams. We know the limit of limit equilibrium, the limitations of limit equilibrium. And this is an adequate method to analyze those dams. We know that we mostly have some stress strain studies to complement those analyses. Significant effort must still be made to evaluate the safety of these dams and prevent new accidents. Next slide, please. I believe that new constitutive models, laboratory tests, powerful softwares, and mainly geotechnical knowledge are required to better safety assessments. So we have a lot of uncertainties. We have different failure modes and triggers. Triggers is quite difficult to analyze either. Limited equilibrium limitations, and significant effort must be made, but new constitutive models, new softwares are going to lead us to a reliable numerical modeling. Next slide. Thank you.
Thank you very much, Tiago, for giving us your position. And we really appreciate that you bring us perspectives on tailings dams. But for those of us who are not Brazilian or not too familiar with these names, for me, is Feijão the same as the Brumadinho disaster? Just so in my mind, I get that sorted out.
Yes.
All right.
Feijão is the name of the mine that is located in Brumadinho city.
Okay, so Feijão is the name of the mine and it is located in Brumadinho. Excellent. Yes. Thank you for the geography lesson. At least now okay. I know what we're talking about. And then also, at some point, when we get into the discussions, Tiago, I'm going to ask you about, you repeated several times, and we do have it, all the panelists will get a chance to talk about it. You said the limitations of limit equilibrium. Do we really know them? So let's just have that in mind. And when we switch to the debate, we'll start with one of those questions. And I've already seen questions coming on the platform, so that's a great sign. We will now move over to Dr. Brent Kolkum, who will tell us his position on numerical modeling. Over to you, Brent.
Great. Next slide. Okay. I'm going to talk a little bit about my unique perspective on numerical modeling, and it comes a lot from the fact that I spent 10 to 15 years when Rocscience was smaller, and I did a lot of the technical support. I saw a lot of the emails coming in from our customers. Even today, dealing with RS2, slide 2, RS3, slide 3, I see a lot of the models. One of the things that always sort of struck me was that I would often get questions of the nature, you know, in the attached model, I'm having trouble understanding the results. Or can you please review the attached model and let me know if the results are correct? And one of my favorites was always simply, model does not work. Why? And these kind of statements, you know, basically boil down to the fact that the user is confused. And why are they confused? And, you know, when talking about problems in numerical modeling, you know, a lot of the problems have to do with the fact that people don't know how to build a model correctly, and they don't know, you know, the process and those sort of things. And in a lot of these cases, you know, when I would look at the model, I would see these, you know, everything but the kitchen sink models, where they've put every possible bit of complexity that they know into the model. Next slide. Now, as Mark Diedrichs mentioned in his keynote, and I fully agree with, is the fact that the idea that you can build one model with everything in it, with all the complexity of the model, you know, that maybe your supervisor has asked you to do. And then from that model gain some meaningful results. that idea is fundamentally flawed. And that's because basically there is no way to properly interpret these kinds of models. They're just too complex. And you know, I would do my best to take the model that a customer would send. And in those days, we were smaller, didn't have as many customers as we do now. Now we have expert modeling programs for customers that are having problems like this. But in those days, I would try to help the user, and you know, usually you know, try to see what they wanted to get from the model, sort of build the model up from scratch with them, and sort of deal with some of the issues that they were having. Now, we've heard a lot about modeling process, and this is an important thing. What is the process, right? We've heard a lot about, you know, starting simple, and what does starting simple mean? Okay, and to me, you know, the process can be, and when you talk about starting simple, the basically you're talking about simple in terms of a given model, meaning, you know, you start with an elastic version of the model. You start with maybe a one-stage model and add all your boundary conditions, and you add all your loading, you keep it elastic, you make sure you've done things correctly, you know, and then build up the complexity one step at a time. Also, process means, what tools do I use? As we've heard, there are many different tools in geotechnical engineering. There are many different numerical modeling tools. You know, we have everything from simple limit equilibrium analysis type tools all the way up to very advanced 3D discrete element multi-physics tools. But you know, how do you've got this huge toolbox, and we've heard that term before, this whole huge toolbox of tools. You know, how do you use them in a meaningful way? And as I've mentioned, you certainly don't go to the far end with the complex. You start simple, you start with the simpler tools, you sort of, you know, gain some idea of how the model is behaving, the important mechanisms, the modes of failure, and we've heard a lot about that as well. Next slide. Okay, so the first item here is, you know, really when I look at it, this sort of forms the basis of rock science. Okay, when we were looking at things back in the 1980s and 1990s, and you know, under the leadership of John Curran and Everett Hook, the whole idea is that basically there is a lot of uncertainty in our models, a lot of uncertainty in the input parameters. There's uncertainty in the material properties, there's uncertainty in the stress properties, the in situ stress properties, there's uncertainty in the geology. There is just a lot of uncertainty. So these tools have to be quick, and you have to be able to do sensitivity analyses, meaning you need to explore different possibilities of different parameters, and it has to be fast. And that sort of instigated a number of our tools, and why, you know, we developed these tools, and Mark had a nice term for them, socialized numerical models, which means that anybody can run them and run them quickly. Ground engineers, everybody could run them. And, you know, basically it would allow them to explore different possibilities. And I think that's a really important fact. And I think this enters into 2D versus 3D and where we have to go with 3D. Okay, that's, you know, now 3D models are, as Mark said, we're once again in that realm where 3D models are not run a lot. They're generally run by consultants, and really we need to get to a point where 3D models can be run by everybody quickly and explore this this different uncertainty. Next slide. Okay, so we talked a little bit about elastic models, and I quickly mentioned that the way that we generally do things, or the way that I like to do things, is, you know, I start simple. I start with a one stage. I look at the initial conditions on something like, say, a slope. I look at the initial stress state. I put in all my, you know, my meshing, my boundary conditions. I always keep it elastic. The last thing I add is plasticity, because plasticity complicates the problem, but it also causes the models to run a lot slower. And really, to me, it's all about speed in getting these models set up correctly. And you know, Joe mentioned a lot about verification versus validation. I'm in the verification stage here, and that's probably because I've seen so many customer models that are incorrect at this basic step. Okay, that basically the first stage, something is wrong. Either it's boundary conditions, or it's initial stresses, or it's something to do with loading or something like that. So it's really important to get this you know, initial setup correctly. Okay, and finally, you know, in any analysis that I do, I always do 2D models, right? And you know, I'm the chief architect of slide 3. I'm the chief architect of slide 2. I would never tell somebody just to do a slide 3 model. I would always tell somebody to explore both 2D models. And you know, sure, I understand that the problems are inherently 3D, but 2D models can tell you so much about mechanism in a quick way, okay? And they are so valuable that I can't understate the use of 2D and 3D. Next slide. Okay, finally, and this is sort of the cool part, is, you know, where is Rocscience going, right? Like where are we going as a company, and what do I sort of envision myself? And we are going 3D, but as I've said, you know, 3D is a can of worms here, and you know, we do need to account for uncertainty. We need to get these things faster. You know, and we need to validate them, right? And we saw that the panel yesterday was fantastic, where we talked about completing this cycle, and we've talked about this for 20 to 30 years, as John Kern and Will Bodden would tell you, that this was a vision long ago, that the ability to take you know, sensor data, or in the case of underground, some, you know, bolt data, extensometer data, and use it to calibrate our numerical models. Okay. So one other thing I wanted to mention before I move on to some of the things that we are working on is the fact that finite element and limit equilibrium, because I do a lot of slope stability, there's, you know, I've seen a lot in this conference, and I would strongly recommend that people be using both. That I always use shear strength reduction with limit equilibrium. They help verify or validate the results. Okay, so that, you know, there are a lot of issues with limit equilibrium. I think we'll be talking about some of those in the future here, but shear strength reduction is just a hugely easy tool to use to validate these types of models. And finally, you know, how are we going to make these 3D models faster? That's some of the interesting things to me. How are we going to get to a point where we can do sensitivity analyses easily with these things? And you know, we are actively working at Rocscience on machine learning. So we have a couple projects on that. We are working actively on high performance computing and our ability to use GPUs and CPUs efficiently. We're working on something called the fast multiple method, which will allow us to do really huge boundary element meshes in not a lot of time, no matrix solving. This is going to be really cool. And I think I mentioned before that, I still have a vision that we'll be able to do things like examine 2D where we're in 3D where we can easily start moving excavations around and changing properties and sort of quickly seeing the effects of some of these changes. And we're looking at data visualization, how to handle huge data and augmented reality. So anyways, I'm going to turn it back over to Reginald and we'll go from there.
Thank you very much, Brent. And thank you, Tiago, Joe, Vic, for giving us your positions. That was really good. Already there are a lot of questions, so I will return to the limited equilibrium stuff, the limitations of limited equilibrium later. I want to get the audience immediately involved. So first question came from Dr. Trevor Carter. He said, I wonder what the panel's thoughts are on Ralph Peck's 1985 comments, which read this: today's sophisticated calculation is too often substituted for painstaking subsurface investigation. And the second part is unwarranted comfort is often taken in the delusion that a range of assumed values, possibly all of which overlook a vital feature, guarantees that the correct results will be bracketed by the calculated ones. Are we here again raising the same concerns, but maybe even more worrisome? Our models may have become too complex to be able to properly validate. So I know it's a long question, but the issue is, are we over modeling? I guess that's literally how I understand it. So who wants to take the first dips at it? Joe, I see you gulping, so maybe you go first.
You're picking on me now. Well, it's been said before that until you measure something, you don't know anything. So you can never substitute investigation and measurement of parameters and just run sensitivities on models with what you perceive to be proper bounds and limits to kind of figure things out. So I agree. They go hand in hand. I'm going to say, when it comes to modeling, the process of building the model is the most important part. The process of gathering the data, understanding the data, coming up with the parameters, building the model, understanding the conditions, it's like the old cliche, it's not the journey, it's the journey, not the destination. And a lot of times, by the time you finish building the model, you could almost pick it up, shelf it, because you got the answer, or at least you should have a pretty good idea of where you're going. It's the process that enlightens you. And when you finally push that button, it's just basically confirming what you suspect or what your expectations might be. You may be surprised, but I mean, the value really is in the journey and not what the program's going to spit up. So yeah, I don't think, if you're doing things carefully and properly, we're never going to substitute investigation by modeling. And if you're going that way, you're just going the wrong way.
All right, thanks a lot, Joe. And so what I'm also going to do to help us go through most of the questions, if not all, is I may not ask everybody to comment on it, but that does not mean if I skip you, but you have some really key insights, just stop me and chip in. That's perfectly fine. But on this issue of the investigations, Professor Stacy, you've been doing this stuff for a long time. What are your thoughts on that? I'll really appreciate your thoughts.
Comment really coming from the mining environment is that very often you actually don't have the real information that you need to collect information, to measure material strengths on those samples from the cores. And it's just impossible really to get that information that ideally one would want to have. And that makes it very difficult to compare real behavior with what is model behavior. And that's why very often mining environment relies on models without the adequate measurement.
Okay, no, thank you for that contribution. I'll move to the next one is actually a comment, but nevertheless, Tiago and Brent, I'll appreciate your thoughts on that. It's from Professor Mark Diedrichs. He says, science is about testing a hypothesis and designing an experiment to prove or refute that hypothesis. Engineers forget that modeling is exactly the same. Tiago, in the space of tailing stuff, do you find this relevant or true, or what are your views on that, Tiago?
No, I totally agree. I think that we can always calibrate and try to create a model that it's as real as possible. So our testers will just give an input to a good model. So we are going to calibrate, and a model to me is a hypothesis. And we have the constitutive models with specific inputs. So I totally agree.
Thank you, Tiago. Brent, what about you? What are your thoughts?
It's a great question. And, you know, when I go in to do a model myself, I generally look at all the factors that are going into the model, and I'm looking at the geometry, and I'm looking at the loading. And before I do any analysis whatsoever, I do have an idea in my head of how it's going to behave, right? I've seen enough of these models. I've seen, you know, enough of different geometries that I get some idea in my head as to how it behaves. Now, that's not to say I'm right, that when I do the analysis that I don't see something different than I had thought. But I always go into it with some idea as to how it's going to behave. And, you know, if I look at a slope and I'm looking at geology and I see a weak anisotropic material, or I see a weak layer, or I see multiple weak layers, right? I'm right away thinking, those are possible failure mechanisms, and I need to explore those. I just don't simply put it all into a slide 2 analysis, hit compute, and away I go with a factor of safety. I explore all these different possibilities.
All right. No, thank you very much. I'm going to, the next one is an opinion. I'm going to try and summarize it, and then I'm going to take comments from the panel. It's from Ahmed Mufti. He's saying that in his opinion, numerical modeling and software in particular, in the near future should be connected to field observation records. And then the whole design construction service of the structure shall become interconnected with automated monitoring and calibration systems. So that's the vision for the future, actually. And we don't want a gap with other industries. So can somebody want to give us your thoughts on that? Do you think this vision, we are close to realizing it, where numerical modeling is automatically linked to field records and calibration feedback? I mean, you know, we spoke about it in the previous panel. Where do you think are we at with this combination of synergies between technologies? Let's start with you, maybe Brent, back to you.
Maybe you could clarify this a little bit for me. Is this the idea that numerical modeling becomes more integral in design, and how do we use it more in design? Yes, I
believe so. Yeah.
Okay. Because this is a great question. You know, the whole idea of how do we use numerical modeling for design, and I have a couple issues with this myself, right? Because I've been asked a lot about 2D versus 3D factors of safety for slopes. And I've been asked, okay, we've got all these design factors of safety for slopes, right? 1.5 for civil, 1.2 or 1.3 for mining, right? But is that 2D? Is that 3D? My 3D tend to be a little bit higher Should my design factors be higher? All these sort of things. And, you know, these are fantastic questions. And, you know, I don't have an answer to it right now.
Okay, no, thanks. Let me move to Tiago, and I'll come to both of you, Joe and Dick, to get your opinions as well. But Tiago, what do you think? Are we close to, you deal with tailing stuff, where field records get into the numerical methods, we get results, we compare with monitoring and stuff. I mean, we've had a classic unfortunate incident not too long ago, the Feijão Dam. Any thoughts on that? Are we close to implementing this?
Yeah, we are reaching a level of sophistication, especially in monitoring systems because of technology. And I think to have a good model, we have to calibrate also with the monitoring system. So technology can help this. Automated recording of field behavior, I think it can help us to model and calibrate some behaviors of structures like tailings dams. I think it's a natural way of technology to help us to understand the behavior of some structures.
All right, excellent. Dick, your thoughts?
I'd like to go back to the design process. And the last step of that involves monitoring. And if that monitoring shows that the behavior is different from what was analyzed or modeled or predicted, then actually you need to take the design process back some steps and perhaps reevaluate things, change the design in some way. And that would probably involve revised modeling.
Okay, so do you think our technology is close to doing what you just described?
I think it's certainly improving. And with the monitoring techniques that are available now, you can get an awful lot of data on the behavior, you know, during excavation and so on. And that can feed back into the design process and the numerical modeling process as well.
Okay, thank you very much. Joe?
Yeah, I mean, this has always been a loop. It's never been, you know, you start here and you stop here. You have to circle back. You have to check. I would say, I think we're a little bit closer to that than the question implies, because I'll give you an example. In open pit modeling, we used to rely on prisms, and we try to calibrate slopes on 3 or 4 prism behavior, which are just spots. And if you happen to have a prism that's sitting on a moving block, it doesn't reflect what the slope is doing. So more recently, we don't do that anymore. We take LiDAR, we take a cloud, we take a deformation cloud, and we try to match the behavior of the full wall, not just particular points. So that's the kind of thing that you need to do these days, because you're trying to capture, I mean, in open pit, you're looking at stability of the full wall, you're looking at stability of a final pit. So you got to take the whole into consideration. The tools are there, and I agree that the monitoring techniques have advanced tremendously, but I'm starting to see them being brought into the analysis and doing a calibration based on those larger sets of data rather than just a couple of points sitting on a couple of blocks.
All right. No, thank you very much, Joe. Now, the next question is coming from Edna. I believe it's from South America, Edna Montia. She said, excellent presentations. A question especially for Professor Stacy and Dr. Kolkum. Could you mention, according to your criteria, some examples of which geotechnical problems are better and efficient to model in 2D or in 3D? So when is it best to do it in 2D and when is it best to do it in 3D? Do you have, from your experience, some criteria you use?
I think that what Joe and Brent have said is very valid, in that it's easy to start with 2D. And I think that that is probably the best way to go, is to start with 2D elastic, and develop from there, and then take it to 3D. So often we actually don't even know what the boundary conditions are. That's the 3D in situ stresses. So in many cases, models are analyzed where we've just assumed what we think those stresses are, and that's also a significant shortcoming. But it depends. You know, if you're looking at a long tunnel, 2D would be fine. If you're looking at a long slope, 2D is probably okay. But if you're looking at near the face of a tunnel or at intersections and so on, those are definitely three-dimensional problems. And your stresses can change there locally as well. So it's necessary to take into account 3 dimensions in those particular situations.
Thank you very much, Professor Stacy. Brent, your thoughts?
Yeah, I would agree completely with that. You know, I don't think the question is so much when would you use 2D versus 3D, right? Like, to me, it's you always use 2D. I would always use 2D. The question is, when do you move from 2D to 3D, right? When, and I think Dr. Stacy mentioned, you know, answered that quite well, in that, you know, there are cases, you know, where the 3D nature of the geometry is such that with today's modern 3D analysis tools, it's quite easy to do an analysis of these types of things. And I would recommend moving to them. You know, the cases, as he said, like the end of a tunnel, or you know, if you're doing a braced excavation for a large building or something like that, where it's not really 2D, right? That, though, you know, that's when you want to move to 3D.
All right. No, thank you. The next one is a comment. I'll quickly read it, and then I'll have a question for Tiago. And then after the question to Tiago, which everybody is free to comment on, Dr. Alison McQuillan also has a question for all of you. So once I'm done the question to Tiago, Alison will come in and ask that question. But Dr. Nidbalski said, Dr. Kolkum, it was excellent. The principles for every beginner with numerical programs in geomechanics, but also for advanced and for experts who forget about the basic rules. So the rules you provided, Dr. Nidbalski is saying that's great. Even professionals, even those who are very experienced, should still remember the basics of modeling. Thank you. Now the question to Tiago is, you spoke about Norse and some of these really complex tailings behaviors. How can you start simple with that? Norse is complicated. I mean, how do you start simple with a problem like that?
Yeah, that's a great question. Yeah, for dam decommission and design, for example, we start with basic limit equilibrium, assessing the factors of safety, and then we complement with simple finite element analysis. So we start with Kolkum, with drained behavior, and always calibrating with monitoring systems. So not necessarily the North End will lead out to the better results, and after Kolkum, we model with vertical stress ratio, for example, and we are trying to calibrate the results of the model with the monitoring system, and step by step. And the North End, to me, is the last step to try to model a complex behavior like this. So I always start with basic limit equilibrium, but complementing with another complex analysis.
Okay, thank you very much. Alison, would you like to ask your question now?
Thanks, Reginald. Everyone on the panels this morning my time, has talked about sensitivity analyses, and there's not a one answer model. I guess this sensitivity analysis relates to the variance in model inputs, be it material properties, stress range, structure. The panelists' thoughts on a confidence chart being reported with numerical models that gives the audience or the reviewer an indication of the actual variance in these inputs, so they get an understanding of the representativity or the accuracy of these models. So Dr. Stacy, you mentioned many times that stresses are assumed, so your thoughts on a confidence chart with the model inputs and whether they're assumed, measured, or varied in the results?
That's a challenging question. I don't think I have the answer in terms of a chart, but it would be very nice to have a systematic way of evaluating the confidence that one has in the analyses that are carried out, which would include all the input data, the value of the analyses that are carried out, because it could be 2D, 3D, it could be different criteria and so on. And those need to be evaluated as well. And then again, as I say, it all needs to be confirmed by the monitoring at the end of the day.
Thanks.
You. Yeah, Alison, go ahead.
Oh, sorry, I was just going to open to the other panelists for their, maybe Joe, from your perspective.
Yes, so sensitivity, let's break it down a little bit. What we're trying to find out is which parameters really control the mechanisms. You may start with a broad range of parameters that exist in your model, and by varying the ranges of these parameters, you'll quickly find out that this parameter this is pretty insensitive. I don't have to worry about it. I have to have a reasonable number for here, but it's not controlling much of the behavior. Whereas another parameter is completely dominating the behavior. So that's basically an indication to you that you must go and collect more data on that parameter. That's the benefit of the sensitivity analysis, is to show you where your deficiencies are, which parameters are controlling, and that you need more data. So only with more data then can you start doing some kind of reliable analysis and rely a little bit on your results. So the first step of sensitivity is just to rule out the parameters that are basically the models is insensitive to, and then figuring out where do I need to go more data, where do I need to go and get more data, where should I put more money. These investigations, we all work for clients. You ask them money for an investigation is like pulling teeth. And to this day, I still don't understand why they would not invest in a proper investigation. I think it was Suzanne Lacasse who said, you always pay for the investigation. The question is, do you pay before or after? So, it's the identification of the parameters that you really need to get and wrap your head around that's important on the sensitivity analysis.
Great points. Brent, your comments?
Yeah, I would totally agree with Joe. I did a model last year. It sort of as Joe was speaking, I was thinking of this model. And the model was basically a slope with joints, and the joints were somewhat horizontal. And, we were looking at using piles to stabilize the slope. And depending on what we chose as the initial stress field, right? Horizontal stress in particular, and its orientation, and how we actually constructed the initial state, meaning settling it versus putting initial stresses into it. There was a factor of 2 difference in the amount of load put on the piles, just because in one case, the joints were near their ultimate capacity for slip, and in other cases they weren't. Okay, so basically load was either transferred to the piles or it was eaten up by the the joints. So I'm listening to Joe and I'm thinking, you know, as somebody that was reviewing this, I would want to know that that was the parameter. I need to go out and measure stress field. I need to go out and figure out what the stresses are in my slope if I want an accurate measure of the amount of load put onto these pods.
It's complex. Diego, your thoughts before I hand back to Dr. Hammah?
I think everyone just told you everything, but especially in dams, for example, running a sensitivity analysis is quite important because we can vary, for example, the water level of the reservoir, and you can see if the problem of instability is on the foundation of the dam or no. So if the water level has a great influence on the factor of safety, we can install more piezometers, for example. If it is the foundation, we can carry out some complementary tests. So for me, it's quite important.
All right. Thank you very much, all panelists, and Alison for your great question that had us all thinking very hard. There are a couple more. One is a comment, and then I'll move on to another question for the panel. Masood Raju is saying that there's a topic he's, believes we should address in geomechanics, and that is 2D versus 3D constitutive models, not just the models we build, but constitutive models that actually take into account the sigma 2, the intermediate principal stress, that is typically ignored. And in fact, Masood believes that ISRM should set up a commission on constitutive modeling. Any thoughts on that? Joe, Dick, Brent, you specifically. Tiago is soft stuff.
I can make a comment. One of the slides I showed indicated the importance of taking into account sigma 2, the intermediate principal stress.
Right.
And work done by Diskin and co-workers at University of Western Australia in terms of rock fracture shows that fracturing will develop relatively easily in the plane of sigma 1 and sigma 2, particularly as sigma 2 increases. But I think, if I remember correctly, it's even when sigma 2 is only about 10% of sigma 1. If sigma 3 is a low value, as it would be on the surface of an excavation, you can get the fractures propagating in the sigma 1, sigma 2 plane. And that's, I think, explains why one gets slabbing in tunnels, particularly under brittle rock conditions.
All right. Well, thank you very much. Yes. Any other thoughts?
I was just going to add that, I mean, probably one of the reasons we are not where we should be with intermediate stress. I don't know how many outfits, labs, or that have the ability to test triaxial states. I was fortunate to have that capability when I worked with Schlumberger, and we tested a lot of stuff at TerraTech, and they had polyaxial cells where you could actually test three-dimensional states or stress states. So I think it's a little bit of the limitation of the testing machines and the testing apparatus. We don't have a lot of those, and because I think it's been hidden because we don't measure it. We haven't had a capability to measure it. I can guarantee you if we had the capability, we'd be paying a little bit more attention to it.
Yeah. Well, thanks. Brent, anything to say about 2D, 3D constitutive models?
Let me just call Ali Reza here and ask him. Unfortunately,
you can call a friend.
Unfortunately, that's a little bit outside my area of expertise. Sorry.
Okay, that's okay. No, thanks a lot, Brent. We really appreciate all your inputs and letting us know that that's not where your expertise is. We've got to move and ask other people. Now, Tiago, we excuse you from this question because we had a more difficult question for you. And that question is directed to you. It's coming from Lunga Mapekula in South Africa. Thank you so much to the panel for this session, very informative. Tiago, what are the typical signatures that one would expect from tailings in a numerical model? And how much do these signatures differ from for your various types of tailings? So that's the question to you, Tiago.
Yeah, we have some signatures on the basics from the first division between the tailings. Is contractive or dilative behavior? I think it's the first one. And when we have contractive behavior, we have different types of contraction, varying, for example, this post-peak loss ratio, how the tailings behavior post-peak. It's brittle, it's ductile, so we have this type of behaviors, how the increase of pore pressures occurs during shearing, for example, and based on a CPTO test analysis, for example, we see the friction ratio, we see the pore pressure, the state parameter, and we see all the information about the CPTO and try to divide those layers in the section we are analyzing based on the signature. So there's not a specific signature. Each case has different behaviors. So we are trying just to separate and not just understand that data is homogeneous, that it's not. It's divided by layers because of the hydraulic disposals. So that's what we do by trying to understand the different behaviors inside this huge mass of tailings.
All right. Thanks a lot, Tiago. Now, this is coming from Dennis Ball. Today, I saw 3D models where there appeared to be no change in soil parameters and little, if any, change in topography. So it seems to me that a 2D model will be sufficient. Am I missing something? I think it's what Dennis is saying is true, isn't it? That if there's not much variation in that out of plane direction, no geometry change, no parameter change, then you might as well just do 2D. What do you think, everybody on the panel? Do you agree with Dennis? Brent, you're muted.
Well, I was waiting for somebody else, but you know, it's a good question. Number one, I'm not familiar with the model, so I would have to see the model itself to make a firm statement on it. But you know, certainly if there's no variation in results from a 2D analysis along the length of a model, like for instance, a tunnel, right? And you're going along the tunnel, then yes, then I would say that a 3D model would not be of any benefit.
Joe?
I think what's missing in the question is, you know, talking about no change in topography, no change in parameters, but you know, what is the geometry? And that's what Brent was trying to say. Yeah, so your environment is uniform, but what are you trying to build? If you're trying to build a long tunnel, I agree. If you don't have that, then you have to pay attention to geometry. But yeah, I mean, there's many instances where a 2D model will suffice. I tend to agree. You should not just run a 3D model just because they exist. You know, it's just simple as that.
Hey, thanks, Joe. But by the way, Joe was my TA in university, and he always knew the answers to these things.
So now you gotta blame me for everything you've done now, right?
That's a good one. We are almost at the end, so we might have enough time for 2 more questions. This question, Brent, is more for you. Can we bring RS3 and slide 3 closer to the ease and usefulness of Settle 3D? The borehole and stratigraphy feature in Settle 3D are great. That's a comment from you, from Dennis.
Oh, yeah, That's a great question, and it's at the top of my mind. That, you know, to me, it's all about, and some people might think me dangerous, but you know, it's all about making these things extremely easy to use. And you know, let's be honest, 3D models used to take you weeks to build and sometimes weeks to run. And you know, we've gotten it down now to, you know, in the day ballpark, couple days, you know, depending on the complexity of the model, right? Those are gross generalizations, but I think we've just started. I think in 5 years from now, it'll be even quicker, faster, and there'll be much improved technology for actually building these models very quickly in the same ease of, well, maybe not as easy as Subtle 3 because that's pretty easy, but certainly a lot easier than they are now.
All right. No, thank you. Just a comment on the 2D versus 3D constitutive models. I see a comment by Professor Mark Diedrichs. He says, the apparent importance of sigma 2 in most of our models is likely far lower than many of the other components of our models that we approximate or ignore. So that's just a comment from Professor Diedrichs. I think I'll come back and maybe take a comment on that very shortly. But yeah, we just have a minute or so. This one was important because it's different from all the other questions asked. It's coming from Mahmoud Mohammed from Simon Fraser University. He says, I noticed from the entire conference, almost all papers did not take structural geology in their modeling adequately. Please share some thoughts of the role of structural geology in numerical modeling. It's for all panelists. Please have a go at it. And Alison as well, because you also do that kind of stuff. Alison, who would want to take the first dips at it?
I'll go.
Okay.
You do not have a geotechnical model until you have a geological model, period, right? If you don't understand the geology, you know, you might as well quit, because, you know, geology equates to geometry, equates to behavior, equates to everything. So it's important to start with a good geological model, no questions asked. Now, people do simplify things. Sometimes if you've dealt with some data that comes from the mines, from the geologists, it's extremely hard to deal with. It's messy, it's dirty. You know, they're not thinking of modeling, they're just looking at what they have in terms of geology. So it's a hard job to clean that stuff up, and people make simplifications. But yeah, if you don't understand the geology, even the genesis of your site, then you're missing a lot.
Thank you, Joe. Dick, any thoughts on that?
As I indicated, to take into account the jointing in the rock mass is essential in looking at the behavior of the rock mass, and the model should take that into account. So I don't understand the question from that point of view, because
okay.
Because I think we've all answered it to a certain extent, indicating that it's so important to take into account the structure of the rock mass. And that's the geological structure.
Okay. No, thanks. Tiago, you deal with TSFs, but you guys have structural interfaces. You have planes of weakness, maybe Linus or something like that. In your practice, in those models, do you actually take those into account?
Sorry. And I think that this case of structural geology is quite important too in hydrogeologic issues. You know, we must understand how is the behavior of the water inside the rock mass also. Mm-hmm. So it's quite important too.
Okay, so in your stuff, but have you seen models of TSFs where they've actually put in some of these structures in the foundations?
Yes, of course.
Okay.
When we deal with dams, we try to do a good geological model, geological and geomechanical model as well. So we base on the structural geologic model, and then we develop it to a geotechnical model too. So it's quite important for us too.
Okay. This is an interesting question, and it's one I love because it agrees precisely with my position. But let's hear it. It's coming from Ian Williams in the UK. Why not construct our models in 3D and generate a 2D model as cross-sections through the 3D model? Wouldn't that be easier? Any thoughts on that? Go ahead, Brett.
Yeah, that's a great question. And, you know, certainly it's very possible. Like a lot of 3D software now, not only from Rocscience, but from other software vendors, have the ability to pass sections between their 3D and 2D equivalent programs. And, you know, it certainly is quite easy to start, say, with a slide 3 slope and look at sections all around your pit and sort of see what the 2D factors of safety are. And you sort of think to yourself, you killed 2 birds with 1 stone, right? Because you construct your 3D model, then you don't have to worry about taking sections because the program does it all for you, right? So it's a, you know, if the end is that you're going to have a 3D model, you reduce the amount of work by constructing it first and then using the built-in tools to construct the 2D sections. Now, having said that, is that the right modeling approach, right? Is that the correct way to do things? And I would say that, you know, maybe in slope stability, possibly, but, you know, at the end of the day, usually it's pretty easy to create a section from Leapfrog or Vulkan or one of these other programs and create a slide 2 model. You know, I just can't get past the fact myself that we start with 2D, and maybe it's my age, and maybe it's basically I find that I can get so much information from that 2D model with mechanism, right? That I can, you know, determine what the mechanism is before I go to my more complicated 3D model. And I've always sort of thought that that was a hugely important thing. But I do know that the other way is you know, you know, maybe Reginald, you could speak to it because, you know.
Okay. Actually, Brent, in slope stability modeling, I have seen it work very well with open pits and stuff where the geology is all over the place. You're actually building 3D because when you're taking 2D cross sections, it's not very clear where your critical cross sections are. And you can actually miss out on that. So when you do the 3D, and then you just get some answers, it shows you the hotspots, you take your 2D cross sections. Actually, that can give you a lot of information. So in some of the things I have seen, especially recently, it's actually quite helpful to build in 3D and go to 2D from there. I wouldn't say it's always the case, you're absolutely right, but in some cases I have seen that works very well. So that's the little I have to add to that.
Yeah, and it might be, you know, and I have a number of cases in my history where I've needed 2D models to properly see mechanisms. And it might be, you know, in all these cases, it was finite element models where the actual behavior was very complicated. And it might be that, you know, slope stability is such that it is a good problem to do it in reverse because it's not as complicated. But, you know, I'd like to hear from everybody else on their position. I know Allison actually builds more 3D models than I do.
I'd agree with Reginald. And also, I think what Joe said initially about having things not as absolute, but as relative. So I found that building your 3D model initially can give you a relative indication of where your critical areas would be in your pit. And then the 2D analysis to focus in on that and validate what you're seeing in 3D. But also 3D can give you or capture where you do, in particular in open pits, have where your orientation of structure influences your likely failure mechanism, or is a wedge likely to fail or slide out relative to the orientation of the pit slope. starting with 3D can identify those more critical areas and then see, yes, 3D would be more valid, and then even validate that with kinematic analysis. So I'm going to sit on the fence and say an integrated approach. But it's all about understanding, I guess, as Dr. Borden's alluded to in his comments and in his paper, but having an indication of the problem that you're trying to solve initially before selecting the right modeling tool or the most appropriate modeling tools.
All right. No, thank you very much, Alison. I'll take two very quick responses from Dick and Tiago on this, and we will end our session. So, Dick?
Okay. In the very early stages of, or early times of numerical modeling, what we used to do was to have a very simple three-dimensional model, because that's all we could model at that time because of the power of computers and so on. But we used to combine that with a range of two-dimensional analyses, which could be at different orientations. So we were looking at the problem in 3 dimensions with the different two-dimensional sections through the problem. And then we'd sort of match that up with an overall simple 3D model, just to check that everything was, you might say, hunky-dory.
Okay, no, that's excellent. Thank you. Tiago, your brief thoughts before we conclude? We just have a couple of minutes left.
I have worked in a 3D analysis of dams that was very interesting. One of the case, the 3D analysis indicate that the critical region is on the right abutment. So when we analyze in 2D, we generally put the cross-section on the axis of the dam, not on the abutments. So the 3D indicated some places that we didn't analyze naturally, thinking just about in 2D. And another one, it was just like that. The 3D analysis indicated some place that it's not common. And we then create a cross-section to analyze in 2D in a different place. So the 3D is quite important to me in this we can analyze other regions that we can't see in 2D analysis.
All right. No, thank you very much. This has been an excellent panel. You guys have given us wonderful opinions. And there are still some questions that and comments that I would have loved to share. What we'll do, as we promised, will be take these comments and questions and we'll collate them and send them out to you. Give us some comments so we can give feedback to the audience participants. But Professor Dick Stacy, Dr. Brent Kolkum, Dr. Joe Cavallo, Mr. Tiago Brettas, Dr. Alison McQuillan, thank you so much. And I look forward to see you all at the closing ceremony, which will be in another 5 or 10 minutes. So see you at the closing ceremony. Thank you all so much.
Thank you,
and
Reginald.
all the best.
We'll see you there. Thank you.
Thank you.